So I'm Sarah Kelley. I'm a data scientist with the American Institutes for Research, where I work on a wide variety of data science projects, most focusing on understanding innovation in the nanotechnology space and working with patent data. And this is my co-author and evidently twin sister, Claire Kelley.
Hi everybody, I'm Claire. I'm also a data scientist at the American Institutes for Research. My work focuses mostly on data pipelining and machine learning in the healthcare space. So I'm interested in taking a break from my general work on healthcare availability and access to work on this project about patent citations.
Okay, I should have practiced this first. Lovely helper here. How do I go?
Got it.
There we go. Next slide.
It's this one.
Okay. So what we're going to be talking about today is patent citations. So if some of you are thinking that sounds like the most boring topic in the world, let me try to tell you why we might be interested in patent citations. So for those of you who are not familiar with the patent space, much like academic articles which reference previous articles on whose work they build, patent applications also cite previous patents whose innovation and ideas they're building on. These citations are important to the inventors because if you don't cite the correct patents, that can impede the approval of your patent. They're important to the examiners of patents who determine if a patent should be approved or not, because they need to see that the patent is different enough from the other patents in its space to be worthy of its own separate patent. And finally, they're also interesting on an academic level because they help us understand the kind of flow of innovation and where the innovations that are leading to a lot of other innovations are coming from, which is something that a lot of people in the sort of scientific and science funding communities are very interested in. So there's a reasonable amount of existing research on this. There's a lot of kind of black box applications built by companies to help their own inventors or to sell to inventors to help them figure out their patent citations. And there's a reasonable amount of academic work in this area too, focusing on kind of two main different approaches. The first is kind of a network-based approach, which looks at kind of the author of a patent, their affiliations, and uses that to predict whether their patent will be cited by another patent. So for example, an inventor at a very well-known company and an inventor who is widely cited and sort of considered an innovator in their space, we would expect is more likely to be cited than, you know, Joe working out of his garage in Kansas City. So these models kind of focus on the relationship, the existing relationships between patents and their citations. There are also sort of natural language processing based approaches which try to look for similarities in the core concepts of patents, with the idea that patents are going to be more likely to cite earlier patents that talk about similar ideas and even that use the same language, because it's pretty well known at this stage that patents are more likely to cite other patents that come from the same kind of sub-discipline and so use the same kind of terminology than those that come from that may be equally related but use a slightly different set of terms. And I kind of talked about that already. A lot of the existing approaches also take advantage of keyword search. So one of the things we were interested in here is seeing if we could generalize this to not require any human input. So not in the sense that the inventor wouldn't have any input to their patent, because we're not quite that advanced yet, but in the sense that the search itself wouldn't rely on a keyword strategy like many of the existing approaches do.
One of the big problems with the keyword strategy is that it leads to this within field bias. So if I was to write a patent and I know my own subfield very well, I will be using keywords that match to other people within my subfield. But I might be missing the keywords that match better to similar patents in other subgenres. And so it leads to this compounding problem where all the patents in one field cite each other in a sort of circle pattern, and they aren't citing relevant research from without that subdiscipline.
which also has implications for innovation because we know that more cross-discipline, kind of cross-pollination of ideas is productive for coming up with those really game-changing innovations.
All right, so we wanted to provide you a couple of examples so you know what we're talking about. Obviously, the text of a patent is very long. In this example, we're focusing on the titles and abstracts of some patents within the nanotechnology space. Don't worry if you don't know anything about nanotechnology, there won't be a quiz. So, for example, on this slide you see the title of a patent, and this patent proposes to talk about methods for arranging nanoscopic elements within networks, fabrics, and films. And on the right-hand side of the screen, we have 3 possible options that we could choose to cite. So if everyone takes a second, reads through those candidate options, we're going to talk about which one you think we should cite.
And there will be a quiz.
So should we choose option 1, golf balls having a low modulus HNP layer and high modulus HNP layer? Or candidate 2, controlled patterning and growth of single-wall and multi-wall carbon nanotubes? Or should we choose option 3, nanocrystalline ceramic materials reinforced with single-wall carbon nanotubes? So we're going to take a vote. So everyone take a second, put your thinking caps on. Who thinks we should choose candidate 1 as the appropriate patent to cite? 2 people. Who thinks we should choose candidate 2? Some more people. And what about candidate 3? Okay, so that seems to win by popular opinion. The answer is in fact candidate 2. Controlled patterning and growth of single-wall and multi-wall carbon nanotubes. Why? Who chose carbon 2 and wants to tell me why they thought that was a good idea? Yeah, you're really hitting at the key of our method here. It's a niche word. So even without knowing the context, I know nothing about nanotechnology. I assume most of the rest of you do too. We know that a word that is very rare and appears in both patents is a stronger indicator of relatedness than matching less important words. How hard was that? Easy, or easy, medium, hard? Probably relatively hard, right? We're trying to make a judgment based on only a couple of words. So what if we had more information? I'm not going to afflict you with reading this out, but if everyone takes a second, reads through this abstract, we're going to talk about how to match this by the abstract as well. So this is even worse to read than the documentation of Spark. All right, so that's the abstract to go with the same patent. And now we have 2 other candidate abstracts that we're going to think about which it might be related to. So this is the first candidate. All right, everyone falling asleep? Okay, next one. This one's shorter, I promise. Okay, so again, let's vote. Who thinks that the patent is most related to candidate 1? Minority opinion. And who thinks it's most related to candidate 2? All right.
The majority votes for no idea, apparently.
Yes. And the few brave people that voted for candidate 1 were correct. The reason that we're having, as humans, more difficulty with this is as the language gets more complex and the abstracts get longer, we tend to get lost in the details. One of the possible applications of this whole project is to help out research scientists who are doing the same thing you just did and having their eyes glaze over as they read through nanotechnology jargon over and over again. This is, I have to say, one instance in which I have to admit my sister was right. I thought that identifying patents based on the text of titles would be more accurate because titles provide a more focused look at what the patent's about. It turns out actually taking into account both the abstract and the title is more accurate. Okay, so to move on to the fun text stuff. For this project, we used mostly a Google-based infrastructure. We're using Google Compute instances for all the calculation steps. We're using Google BigQuery to store the data, and Google's Cloud Storage as an intermediary for storing files. One of the big struggles within the text processing space, and particularly to do with this project, is simply the volume of information we have. So the US government provides patent data in bulk in XML files. This is helpful to nobody. And so a big part of this project was collecting and aggregating those XML files, passing them into a flat format, and then storing and dealing with all the text. For this project, we initially looked at about 250,000 patents, which, if you imagine how dense the text and how long the text of some of these patents can be, ends up being quite a big data problem.
So there are a lot of patents. There are a lot more than a 250,000 patents. So today we're just focusing on patents in the nanotechnology space. And the way we did that, we have filtered all of the available patents, focusing on only patents that meet kind of a complicated keyword criteria for nanotechnology. If anyone's interested in the details of that, ask me after, and I can link you to the paper that we used to develop our sort of limiting strategy. Okay. So the first thing we're going to touch very briefly on that we ended up not using for our results but explored first, as this is a pretty common approach in this area, are a keyword and topic modeling based approaches. So the idea with topic modeling is that we can divide our patents into separate topics and then really narrow our search space. So we divide our 250,000 patents into 200 different topics, and then we only need to look within a topic for possible candidates to be cited. Now that sounds really nice in theory. In practice, it doesn't work so well. If we look first at the topic modeling, which is second on the slide, but if we look at first topic modeling, we're evaluating this simply basically based on the percentage of citations that are within that topic. So obviously, if we only have 10 topics, we're going to have more citations within topic citations. In fact, we'd expect, if the citations were distributed randomly, we'd expect to have 10% of the citations from within that topic. In fact, we find that if we look at the combined text of the patent and abstract, which tends to be the most accurate method, we have about 25% of the citations are within topic. So the topic is telling us something, but they're not discrete enough that we can consider only patents within a single topic as our search space. And as we increase the number of topics, which makes this technique more useful for narrowing the search space, we decrease, obviously, the number of patents, the percentage of citations that are within those topics. We kind of hit the optimal level was 40 topics, where we had the kind of it's narrowed the space enough to do more complex things if one wanted, but still had a reasonable percentage of the patents within the topic. But even that is not good enough to really use in practice. If we compare this with keyword search approaches, in 3 we looked at nanotubes, DNA, and graphene. And if you look at topics defined by the presence of those keywords, you'll see that for some, like nanotubes, you've got a slightly higher that field tends to be more condensed, with more of their citations containing the same keyword. But even that isn't looking so promising as a way to limit our search space. So we're really focusing on building an approach that can be used across the whole set of nanotechnology patents, not just within one particular area. So the first approach we're going to discuss is a cosine similarity based approach. So this is a pure natural language processing approach. This doesn't consider at all the existing citations of the patent, the number of citations to a given patent. All we care about is the similarity between the language used in the two patents. So I'm going to assume that some people are probably very familiar with this kind of measure and other people are not. So I'm going to kind of go into some detail about how it works and hopefully not bore everybody too terribly. So As I just mentioned, this approach is based on just the language, which has some advantages because it doesn't perpetuate existing issues or biases within citation patterns because it doesn't favor more heavily cited patents or patents from well-known companies over any other patents. It just bases it on the language similarity. But also has disadvantages in terms of it will be very vulnerable to if there are different kind of linguistic patterns between fields. It's not necessarily going to pick up very well on those similarities. And there are a couple of approaches we could use relating to word embeddings that might help with some of those issues that we didn't get a chance to explore for this presentation. So, the way this cosine similarity model works is first we're converting the words, in this case the combined text of the title and abstract of the patent, to a vector space representation. So to start with that, we are converting our documents to a bag of words representation, and then we're counting the frequency of each term in a given document. So this is the sort of term frequency part of the term frequency inverse document frequency that we're building up to. So we're representing each document as a sparse vector of term counts. So how many appearances of the word nanotube, DNA, graphene, across the entire vocabulary of the whole corpora, all of the patent data that we have. So that's a very large, very sparse matrix there of size, number of documents times the length of the vocabulary. Hopefully that's relatively easy for people to envision. However, as our very clever question answerer earlier in the session pointed out, some words are more helpful than others. We gain a lot more information from knowing that a patent mentions nanotubes than that it has the word the in it. Patents that both have nanotubes are more similar than patents that both have the in them. Hopefully that's relatively intuitive. So, as well as considering the term frequency, we want to consider the inverse document frequency. So that is, in our little equation here, is the where we're going to divide by the number of documents that contain that term. Adding one, of course, so we don't have a zero division error if we have a term that's not in the corpora. And this leads us to our term frequency inverse document frequency measure, which is the term frequency in that document multiplied by the inverse document frequency of that term. So what this basically does is it favors rare terms over common terms, based on that kind of intuition that we discussed earlier about the more unusual terms telling us more about the similarity of documents than those more common terms. We also, if you've been paying attention to the math here, we also don't want longer documents to be favored, because if we just consider the term frequency, then longer documents will have on average a higher frequency across all terms. So we'll be saying in general that longer documents are a better match than shorter documents. Now, there's no real empirical reason why we would want to do that. So we're going to normalize normalize our matrix in a row-wise fashion. And so that we're basically getting the fraction of words in the document that are that particular word rather than the raw frequency. Our Python implementation of this, we used GenSim, which has some very nicely optimized code to do this much faster than my handwritten code did. That was slightly demoralizing, actually. Where we create that term frequency inverse document frequency matrix, and then we score in this first chunk here. Do I have a pointer? Yes. Okay. Where we create a dictionary and use that to create a term frequency inverse document frequency model, and then we, in our second chunk here, we score a sample of 2,000 patents that we're interested in. We score them based on their similarity to all of the other patents in the space, and we end up predicting the 20 most similar patents. So if we predict the 20 most similar patents based on just this cosine similarity approach, those 20 most similar patents includes on average 10% of the patent's actual citations. So nowhere close to 100% accuracy, but that's a reasonable start for something that is very easy to implement and requires no kind of domain knowledge or extra pre-processing whatsoever. So this is a sort of pure natural language processing based approach, and we're interested in supplementing this in our next step with an approach that considers the existing citations of the patents.
All right, so one of the problems, in addition to identifying appropriate citations, is using the information that the existing citations give to make our process even better. So in this data set, we know what every nanotechnology patent since 2001 has cited, and we should be able to use that information to help us when we have a new paper, check whether our citations are sufficient and recommend additional new citations that we haven't considered. So recommendation engines have been something that's been gaining popularity in industry. For example, I'm sure everyone's seen on Amazon or Netflix, you have the customers you might also like section, which is basically a representation of this matrix factorization model in which we look at previous user product pairs, or in this case, previous patent citation pairs, and use that to suggest novel citations. So, brief background on matrix factorization. Basically, we consider the data represented as a matrix where each row represents a patent and each column represents which patents it cited. This is obviously a large matrix, right? If we have 250,000 patents, it's a 250,000 by 250,000 matrix, which makes nobody happy. The idea behind this is to decompose it into a set of latent factors. If you're a statistician, you'd call them latent factors. This is the decomposition we're talking about in the factorization part. There are not a known number of latent factors. So going back to the problem we had with topic modeling, we don't know how many distinct groups of patents there are. And the best way to tell that is by in our parameter search. So we're going to start with the 40 latent factors that we decided was best based on the topic modeling, but that's sort of the art part of data science rather than the science part of data science. So in this case, we're considering the decomposition of the preference matrix R into a vector X and a vector Y, where the X represents the latent features of a patent. For example, you might consider this is how closely related the patent is to graphing technology, or another latent feature might be patents that are closely related to electroconductivity, say. Similarly, there's a vector Y which describes how closely or how likely each patent is to cite that particular topic. Both of these vectors are unknown and are initialized at random when we start the algorithm. All right. So initially, we attempted to evaluate this in NumPy because the matrix math isn't actually all that complicated, but this quickly leads to an out-of-memory error. So we turned to Spark to handle the distribution of this across several machines in order to avoid that out-of-memory error. Luckily, MLlib has some very friendly matrix factorization implementations, and the about 6 lines of code you see there actually completely runs a implicit matrix factorization model. Basically, the key here is we're setting the rank, so that's the number of latent factors, the number of iterations we'll allow, and a confidence factor. Then you train your model right there. It's important to note that we are considering this as an implicit model versus an explicit model. So for matrix factorization models, we have 2 main types. Implicit are typically used where your data represents observed behavior. So in this case, each patent has the observed behavior of having cited another patent. Much like in the more typical commercial sense, a user would have had the observed behavior of having purchased a product. The other method of matrix factorization relies on explicit preferences, which is where the user makes a rating for each object. Obviously, the patent can't rate a citation. So we opted for the implicit method. The next challenge here was parameter selection. So the matrix factorization is evaluated with an alternating least squares methodology. So you'll see that in the literature as ALS. Basically, we alternate, as the name might suggest, between fixing the latent factors for the likelihood of citation and the latent factors for the group membership. So first you fix the vector X and you find the optimal value for Y. then you fix the y while you find the best value for x, and you alternate until you're making either small incremental improvements or you've reached the maximum number of iterations. In terms of parameter optimization, we did this with a combination of prior knowledge, so that's the picking 40 latent factors based on the topic modeling, and a grid search through the other parameters. Obviously, we split into a training and a test set, and we're trying to minimize the mean squared error for the test set. This model is very different from the cosine similarity in that it doesn't take the language into account at all. So we went from a model where we're caring only about the language to a model where we're only caring about previous citations. And as we discussed before, this has some of the limitations that human work does as well. So this means that we're perpetuating rather than preventing that in-field bias. It's also less intuitive to explain. So if you were to provide this as a service, this is coming closer to those black box methodologies than the cosine similarity. In addition, everyone is familiar with the cold start problem. Recommendation engines in general don't do well for cases with little known information. So when we have a new patent, if you only have a couple of citations, it's difficult for the model to know what other patents you should cite. So we see this more as an extension of existing work. So this is a good way for somebody, you could put in a patent that you'd written with your existing citations, and this might recommend to you some new citations that, based on the patterns of other authors, you should also have looked at. So this is more an extension than a replacement. It's also hard to empirically evaluate the quality of new recommendations. In commercial recommender systems, we often solve this problem with A/B testing. So if you own Amazon, you can tweak the parameters and see who clicks more on your recommendations. With your patent, it's a little hard to tweak the parameters and see which were the better citations, because that's something that has to be evaluated manually, which is obviously something as data scientists we should avoid.
However, as a little sanity check, the two methods don't produce totally disparate results. The recommendations from the cosine, the top 20 recommendations from the cosine similarity method and from the recommendation approach have an overlap of about 20%. So about 20% of the patents recommended through cosine similarity are also recommended through the recommendation engine, which is a decent amount of overlap. So clearly, the same sort of core relationships are being found, at least in some cases. So our basic conclusion is that these offer important opportunities to support human citation choice for patents, and we'd like to extend it to eventually to academic articles too, because literature reviews are horrible. But we're still nowhere close to an automatic system that won't require any human input and can do this entirely automatically. Does anyone have any questions? Yes?
So in your recommender system, aren't you recombining the factorized matrices back, right? And then you're doing cosine similarity once again. Is that?
No.
Okay.
So these are two separate approaches. So the cosine similarity looks just at the language, and that is entirely separate from the matrix factorization approach, which is simply looking at the possible decomposition of the patent citation pair. So it doesn't consider the language at all.
Okay, but aren't you trying to? Okay, so when you are trying to find the closest patents, right?
Yep.
What measure are you using?
So in the cosine similarity, we're measuring closeness by similar language. In the matrix factorization model, we're measuring closeness by citations to similar patents.
Right, the latent factors, right?
Yes.
Okay, got it. Second question, and maybe it's a suggestion as well. Mm-hmm. Since you're using an evaluation criteria for your the first method, right? Basically, how many actual citations are there versus how many you could predict, right?
Yep.
Couldn't you do the same thing with your recommender system?
Yes, you could, but we didn't consider that as the best evaluation strategy, because the strength of the recommender system is that it looks at your existing citations and uses that to find extensions, to find ones that you previously hadn't cited. So we're seeing the strength there as the ability to recommend new things that you hadn't already cited.
Okay, got it.
So that's we're supposed to be adding more difference there in a sense, and cosine similarity, we were looking at getting to similarity.
Okay, got it. Right, thank you.
Yeah.
I have many questions, so I'll prune it down to just one for
Okay.
now. I got a little bit lost at the end when you did the factorization. So one question I had was, you had these two latent, you're partitioning the matrices into two different, factoring it into two matrices.
Yeah.
And I wasn't clear on the connection between that and the citations that you're generating that are the new citations.
So, okay. It's a bit hard to explain because both axes of our matrix end up being citations. So the idea behind this is that you are trying to find latent factors for all the columns. So in our case, our columns would be which patents were cited by a particular patent, and also latent factors among the rows. So we're decomposing this into a likelihood of citing a given patent. So the latent citation features is what we're trying to call that vector, and the other vector is similarity among patents. So if your patent cites similar patents to my patent, we are probably sharing one of those latent patent similarity features.
So the resultant matrix you get is actually showing the likelihood of that you should be citing something else?
Yes, and so you can look at, because we chose to use this as an extension rather than a replacement, we're looking at what are the most recommended patents that you didn't already cite.
Okay.
So you can imagine this as other patents like you cited these different patents, just like the sort of Amazon one.
Thank you. Okay, then the second question I had is, did you actually evaluate quantitatively the results? I didn't see a slide talking about quantitative evaluation metrics for this particular part.
So we didn't evaluate, as I think we mentioned earlier, we didn't evaluate the recommender system quantitatively because it has that, because the goal of that is to provide an extension to provide additional patents to cite. So that's difficult to evaluate quantitatively without having someone look at those new citations and see whether they were, and see how good they were. So we didn't make it to that step for this project yet.
That would be the job of one of the unfortunate research assistants.
I was curious if you've thought about combining the models.
Yeah, so going forward, I think one of the things we want to look at is a sort of model ensembles. So that's something that's been really successful in a lot of the natural language processing field, and I feel like there's more we could get into, not just combining the cosine similarity and the recommendations, but there's other methods that we could get into as well, bringing in that networking models that we were talking about at the very beginning, which look at connections between authors and institutions. And I think that would probably be the winning solution in the end, would be one that took into account weighted, a variety of weighted models.
There's been some successful work with author company topic models that combine the kind of linguistic approaches with information about the authors and the companies they work for, both their reputation and their connections to one another, because obviously a Microsoft inventor is more likely to cite another Microsoft inventor than an Apple inventor, probably.
Any more questions?
There's one behind you.
Sorry.
I'm kind of curious with the linguistic similarity stuff, how much idiosyncratic styles of the authors themselves can give you some false readings. I mean, obviously, one researcher is likely to do a lot of things in the same field, but maybe you would, because they use the same sets of phrases, you get your authorship type influences, and I wonder if that would also happen with people who were collaborators.
Yeah, I think auto-citation is probably going to cause some difficulty in the matrix factorization approach. We all know cliques of authors who only cite each other, and that will create sort of false latent factors, basically, that represent membership in this group rather than a true latent factor.
And when it comes to the linguistic analysis, there is that same problem. I think that's mitigated somewhat by the fact that we are taking a term frequency approach here. So the phrases, there's more idiosyncratic phrases probably than idiosyncratic words, but I agree that's a problem, and we should probably quantitatively evaluate how many of your own. That's tricky. That's really interesting because we'd want to look at how many of your own patents are getting recommended, but how often. But is that right? Is that because you're focused on one really specific niche area? So it makes a lot of sense that you'd be patenting a new innovation based on your old innovation. So that's actually a really interesting question. But an interesting question. We'll take that.
Okay, I have a question or two. Depends.
Yes.
For topic modeling, which tool? Probably Jensen?
Yes, Jensen again.
Which algorithm? LDA?
LDA, yeah.
LDA, okay. And how was the performance, the training performance?
The performance was pretty good. I mean, I did not put any effort into optimizing that to go quickly. I just ran it with the different numbers of topics specified. I think it ran overall in about an hour on the 250,000 patents that we're focused on. So yeah, I probably could have got it to go faster if I put effort into that, but for the purposes of this project, that was fine.
Okay, and for Spark, I think for matrix factorization, you have used the Spark
Yep.
cluster for this?
Yep. So it's an 8-core cluster. It converged pretty quickly, less than 10 minutes. But one of the advantages of the Google Compute environment, and one of the reasons we chose that, is because you can scale your clusters in runtime. So initially I had 4 CPUs, that wasn't working well enough. You can add in 4 more and it goes faster then. That's especially important for the hyperparameter tuning when you're running the model multiple times to evaluate different parameters.
Or when your sister prints out the results successively and runs out of space when you're in the middle of running one of your models.
Yes, that too.
Cool, okay. Any more questions? Okay, thank you so much.
Awesome.
Thank you.